Hello, in this video I'm going to solve the following problem for you, which is a problem in the topic of trigonometric numerical calculations. Prove the following identity: tangent alpha minus tangent beta equals to sine alpha minus beta over cosine alpha cosine beta, and use it to calculate the following sum: sine of 2 degrees times sine of 44 degrees over cosine 1 degrees cosine 2 degrees plus sine 2 degrees times sine 44 degrees all over cosine 2 degrees cosine 3 degrees, and this continues until we reach to this fraction sine 2 degrees sine 44 degrees divided by cosine 45 degrees cosine 46 degrees. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do the calculations correctly, the value of the sum will be square root of 2. For more problems of this type, the interested audience can refer to the following playlists. The link to the PDF file that you can currently see on the display is in the description below this video. Okay, so now let us prove the identity first. We start from the left hand side, yes, and then I write sine alpha over cosine alpha for tangent alpha minus, instead of tangent beta I do similarly, sine beta over cosine beta. And then when you look at the right hand side, you see that you have a product of cosine alpha and cosine beta. On the other hand, on the right hand side, you have one single fraction. Both of them will motivate you to take the common denominator here. So I will rescale the first fraction by cosine beta, so it becomes sine alpha cosine beta divided by cosine alpha cosine beta. And I rescale the second fraction by cosine alpha, so it becomes sine beta cosine alpha divided by cosine alpha cosine beta. Now that I have the same common denominator, so I will put the common denominator cosine alpha cosine beta, and then I subtract the numerators. So sine alpha cosine beta minus the other way around. You see, it is the other way around, so it reminds you of the formula, subtraction formula for sine, which is exactly sine alpha minus beta all over cosine alpha cosine beta. Yes, so what I did, instead of this expression, which is the expansion of this subtraction formula for sine, so we are done. So that's exactly equal to the right hand side. Okay, now we want to use this to find the given sum. Okay, now as the problem hinted us, I want to use this identity to calculate the exact value of this sum, and for simplicity I call this sum S. The first observation that I make is I see that this combination, the product of sine 2 degrees sine 44 degrees, repeats itself in the numerator of all the fractions involved in this sum S. Okay, so it is not a bad idea probably to factor that combination out. Okay, so I will write S equals to sine 2 degrees sine 44 degrees, and then I will be left with a bunch of fractions, but all with the same numerator 1. So the first one becomes 1 over cosine 1 degrees times cosine 2 degrees plus 1 over cosine 2 degrees cosine 3 degrees up to the last fraction, 1 over cosine 45 degrees cosine 46 degrees. The second observation that I make is I see the pattern is repeating itself here in all denominators. Namely, I have a product of two cosines in all of them, and the angles that appear differ by 1 unit. So here 1 degrees and 1 degree and 2 degrees, 2 degrees and 3 degrees, and finally 45 degrees and 46 degrees, all differ by 1 degree. Okay, so it might be a good idea, instead of thinking about each fraction individually, let me think about a typical fraction of this type. Okay, what do I mean by that? I mean, let me think about a fraction of this type, 1 over cosine n degrees multiplied by cosine n plus 1 degrees, because all these fractions are of this type. And of course, if I want to consider all possibilities, n starts from 1, 2, and it goes up to 45. So I don't need to repeat it 45 times, I just need to concentrate on doing one of them. So what can I do? On the other hand, because the problem has given me a hint, so it motivates me to compare this one with the right-hand side of this identity. Of course, they are not exactly the same, but they are not that far away, because I see in the denominator I have the product of two cosines, and in the denominator of the right-hand side of this identity given by the problem itself, I have the product of two cosines. If I want to give the role of alpha, say, to n or n plus 1 degrees and beta to the other one, I need to have a sign of the difference of two angles of those angles in the numerator. So this one is not very suitable. I want to have the sign of the difference of these two angles in the numerator. So it motivates me. So if you don't mind, let me move this here. Okay, so what I want to do, I want to write the numerator as the combination I need. The combination I need is the difference of the angles that appear in the denominator. So I would write it as n plus 1 degrees minus n degrees, momentarily of course, and then divided by, if you don't mind, let me write this the other way around, n plus 1 degrees cosine 1 degree, n degrees, and let us see what I have done. The denominator, I have repeated it here in a different order, it doesn't matter. But if I ask you what is this angle, this is n plus 1 degrees minus n degrees, so it is 1 degree. So it becomes sine of 1 degree, but in the numerator I do not have the sine of 1 degree, I have just simply 1. So I have changed the problem. To compensate for that, I have to divide it by sine 1 degrees. Now everything is in order. Yes, so let me just repeat again. So here, if I ask you what is this in the numerator, you would say n plus 1 degrees minus n degrees is 1 degree. So the numerator is nothing except sine 1 degree. Now this sine of 1 degree and this sine 1 degree that I put here, they cancel out, and the numerator will be 1 and the denominator will be the same as the denominator I have. So everything I have done is good. But what is the benefit of that? So if you don't mind, let me write this fraction first. 1 over sine 1 degrees. Now go back to this identity. Give the role of alpha to n plus 1 degrees. Give the role of beta to n degrees. So this becomes exactly this combination that appears on the right hand side. Now that we have already proven this identity, I can use its result. So instead of this, I can simply write tangent of the first angle minus tangent of the second angle. Yes, so this becomes tangent of n plus 1 degrees minus tangent of n degrees. So what I have shown so far, I have shown that any fraction of this type can be written in this form. But what is the benefit of that? Because now I can do this case by case. For example, 1 over cosine 1 degrees, 1 over cosine 1 degrees, cosine 2 degrees can be written as 1 over sine 1 degree. So what I'm going to do now, compare this one with this one we got. Here in this problem n is 1. So I put n equals to 1 in the result. So it becomes tangent of 2 degrees minus tangent of 1 degrees. 1 degree. Okay. The same story for the next one. What is the next one? 1 over cosine 2 degrees, cosine 3 degrees. So according to the formula we just discovered, it becomes 1 over sine 1 degrees, and then tangent of 3 degrees minus tangent of 2 degrees. Is that clear? So what I have done here, because n is 2, I put 2 here. So it becomes tangent 3 degrees minus tangent 2 degrees. And of course, now hopefully you see what happens. This continues until the very last one. For the very last one, I will get cosine of 45 degrees, cosine 46 degrees. This becomes 1 over sine. This also continues sine over 1 degrees multiplied by what? Tangent of which angle? Now n is 45, so I put 45 there, so it becomes 46 degrees minus tangent of 45 degrees. Yes? Now what is the benefit of doing that? I hope that you see what's happening now. So if I add the left hand sides, okay, it is equivalent to adding the right hand side. But what is the benefit of adding the right hand sides? The right hand sides share a common factor so that I can pull them out and add what are left in the pairs of brackets. But this is the very nice idea of this problem, is that if you write it in that way, they will cancel one by one. So for example, you know that the next one will be 1 over sine 1 degrees. The next one will be tangent 4 degrees minus tangent 3 degrees, yes? So if I, for example, start adding them, this will be cancelled by this one, this will be cancelled by this one, tangent 4 will be cancelled by the next one, and this list will continue, and this tangent 45 degrees will be cancelled with the previous one. So what is left? Tangent 1 minus tangent 1 degrees from the 1 degree from the first, and tangent 46 degrees from the last are left. Okay, so if I add them, the left hand side becomes equal to 1 over sine of 1 degrees, and then I will have tangent 46 degrees minus tangent 1 degrees. 1 degree, sorry. Okay, so now I have moved everything we need to the other page. So that was the identity we proved. We were supposed to find this sum. We factored the numerator from all fractions out, and then we calculated the sum in the pair of brackets here, and we got this. Now we glue everything in one place. So S is equal to, I take this factor and write it here, and instead of this expression I just simply write that. So what happens? It becomes sine of 2 degrees sine of 44 degrees divided by sine of 1 degrees, and then multiplied by tangent 46 degrees minus tangent 1 degrees. Okay, but still it's far from calculating the exact value. So the other trick is to use this identity again for this one to go back to sine and cosine, hoping that those sine and cosines appearing from here and these sines can somehow be combined. Okay, so I will copy and paste this first fraction, sine 2 degrees, and then I have sine 44 degrees divided by sine 1 degrees, and then the numerator of this one becomes sine. Now my goal is to give the role of alpha, role of alpha to 46 degrees and beta to 1 degree. So what happens? It becomes sine of alpha, which is 46 degrees minus 1 degrees, divided by cosine 46 degrees cosine 1 degrees. And just one more step. Here, instead of sine 2 degrees, you see, I can use the double angle formula to write it as 2 sine 1 degrees cosine 1 degrees. It is very helpful because sine 1 degrees and cosine 1 degrees coming from here will cancel out these two. So let me write them, and I will simplify them later. So I would write 2 sine 1 degrees cosine 1 degrees instead of sine 2 degrees. Another observation that I can make is that this 44 degrees and 46 degrees are complementary. 44 degrees plus 46 degrees is exactly 90 degrees. So we know that sine of one of them is equal to the cosine of the other one. Okay, so instead of writing sine 44, I can simply write cosine 46. Yes, denominator here I have only sine 1 degrees, and the next fraction 46 degrees minus 1 degree is just 45 degrees, so it becomes sine of 45 degrees, and I copy and paste the denominator of the second fraction as it is. And now the good news is that this sine 1 degree and this sine 1 degree are gone. Cosine 1 degree here and cosine 1 degree there are gone, and cosine 46 degrees and cosine 46 degrees are also gone. I am left with one factor of 2 and one factor of sine 45. So it becomes 2 sine 45 degrees, but this 45 degrees is a famous angle. We know that sine is the square root of 2 over 2, and if I multiply them, so the answer becomes square root of 2. And that's the answer that we are supposed to reach. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.